Dr. Ivo Kabadshow. He got his PhD on error-controlled fast multiple methods and periodic boundary conditions. He has been member of the BMBF-funded SCAFACOS and DFG-funded SPP EXA project GROMEX. He is working at the Zurich Supercomputing Center in the group of cross-sectional T mathematical methods and algorithms. The title of his presentation of today will be An Error-Controlled Fast Multiple Method and the Road to Exascale. Ivo, thank you for being here. You can start your presentation.
All right. Thank you very much, Walter, for introducing me. Can you see my screen?
Yes.
Alrighty, perfect. So yeah, thanks again for inviting me for the talk. Today I want to talk a little bit about the error-controlled FMM and the road to exascale. And this is a three-pronged talk. I will talk a little bit about the algorithm, the implementation, and the next steps, or the steps that are currently going on. And obviously, this is not only work done by myself, but by a lot of contributors, and there's even more contributors in the background. And I only picked a few topics, so you get a rough idea of what awaits when exascale is around the corner. All right, so as Francisco already said, we are dealing with the long-range interactions, the 1/r potential, and our goal basically is to solve it in linear complexity instead of the n-squared complexity. And the most known examples for using FMM or for using fast summation methods would be molecular dynamics, plasma physics, and astrophysics. These are all fields where fast summation methods could be used. I always say the fast multiple method is like a complex answer to a very simple question, and the simple question you can basically see on your screen. You basically have a set of particles, and you want to compute all the long-range interactions. So you want to compute the forces each particle has on all the other particles. So at the end, you end up with an n-squared complexity, because all pairwise interactions have to be taken into account. And if you draw it like a matrix, you see basically all the interactions are taken into account. If you save 1/2 of this triangle because the force is symmetric, well, it still stays n-squared. So you will not gain much. This is just a factor of 2 with respect to complexity. That's not worth talking about it. The other problem with that is if you look at the formula, you see that there is a square root hidden in this expression, and there's also a division. And nowadays, computers are, if you compare it to multiplication or an addition, you will see that the square root or division is quite expensive on top of that. So we have an n-squared complexity and expensive computations, so it's always a good reason to think about something else. What's the alternative to direct summation? I mean, direct summation is a good thing because you get everything down to machine precision. The bad thing is you have like this n-squared complexity. And back in the days, people just used cutoff schemes and said, well, we only are staying in the vicinity of a certain particle with a certain cutoff radius, and you get linear complexity. Problem with that is that your errors is not controlled. You don't have error bounds, and that's obviously something you would need if you want to do physics. So we have to go a different route. And the different route could be fast summation methods. The nice thing about fast summation methods like P2N-FFT, FMM, multigrid, tree codes is you can have basically error bounds, and you can get a complexity up to linear complexity. If you want to categorize the fast summation method, you can do it in the following scheme. You could find 3 groups. The first one would be FFT-based, the second group would be PDE-based, and the last one would be multipole-based. And you can see in the first group, the FFT-based, there's also our P2N-FFT. We just heard the talk about AVAL summation, PME, and so on. And in the group to the right, the multipole based, you will have the tree code and the FMM, and basically a Barnes tree code or tree code is just a cousin of an FMM. They share a lot of the operators, and there's just a little more involved operators in the FMM to go down from the n log n operation to a linear complexity. If you see this in practice, that's debatable. So I wouldn't concentrate too much on if an algorithm is n log n or n. Yes, you will see it at some point, but if you read the SCAFACOS paper carefully, you will also see that it's not like a big prefactor you will see there. Okay, so let's dive a little bit deeper into the basics of the algorithm, so you get an understanding of what the FMM is all about. I try to avoid most of the equations and give you more like a bird's eye view, so we can deep a little bit deeper in the data structures later in the talk. So let's see how this works. Let's come back to the first picture. With the interaction set, and if you start out with an n-squared method that could be printed something like this. So if you have like these 16 particles on a line, for example, or anywhere in space, you would need to set up a matrix like this, and all the interactions would account to your long-range interactions. And if you ask the question, like I did back in the days, if the FMM computes basically the same thing and can get the same precision as the classical one, how would such an interaction set look? And you could basically draw it like this. The interaction between all the particles doesn't stay all the same in the whole interaction, but the interaction set increases with distance. So if a particle is further away from another particle, you can group it together and thereby reduce the amount of single interactions you have. And if you would plot it in a matrix like this, the scheme would look like this. And for those of you who are familiar with H-square matrices, this probably looks exactly the same, and the FMM works exactly in the same scheme. Okay, so the core concept about the fast multipole method is basically particle grouping. If you cannot group particles, then this whole thing wouldn't work. And if we start at the left picture, if you have like two distinct domains, one with n particles, one with m particles, and we only take a look at the interactions that classically would happen between these two clusters of particles, you would have n times m interactions you have to compute. So n times m's square roots, divisions, and all of that. And all the lines here basically represent all the pairwise interactions between these clusters. Now you could go down and basically replace the interaction of a cluster with a pseudo interaction. So where you have on one side a pseudo interaction, whatever this might be, and particles on the other side. You could have it at source, you could have it at target, and the most, in a sense, optimal case where you could reduce the interactions the most would be if you have two pseudo interactions on both sides. How these pseudo interactions look like, we will see in a second, just to give you a rough idea about the method, how this works. It doesn't mean that this is just one interaction with the same computational intensity than one of the gray lines. Obviously, it's a bit more expensive, but there is a method that can represent particles in these groups, in these pseudo interactions, and that's the main idea. If you did see the picture with the grouping, you probably ask yourself, well, if we take a look at the left picture and you have a particle system that looks like this, I don't see any groups, or I cannot make out any groups. So how does this work? And this is where we basically start with the setup of the FMM. So which parameters does the FMM have in order to compute the interactions? And if you have a particle system like this, and compared to the P2NFFT, we are more we do like more the open boundaries, because we are still in real space. So the multipoles and everything lives in real space. So we're not in Fourier space. So for us, it's easier to do everything with open boundaries. Obviously, the method is also possible for mixed boundary conditions. But I explain everything with open boundaries because that's more natural for the method. So the first thing we would do is we would start out subdividing our space. And if we subdivide it in each direction once, you would have a picture like this. And then you would, for example, divide some more. And now you can see you can have groups of clusters of particles inside each box, and boxes technically could interact at some point. So this would be one parameter you would have to choose for a classical FMM, the tree depth. So you set everything up in an octree because we're in 3D space. You could do it in 1D or in 2D, but since we're dealing with electrostatics, we want to use 3D space. So we divide our space up equally into an octree until a certain depth. This would be one parameter. A second parameter is the well-separatedness criterion. Unfortunately, due to convergence reasons, boxes directly sharing an edge or in a corner cannot interact. So all the gray boxes you see in the left picture where WS is equal 1 cannot interact with this box A. So therefore we have to ignore them for the moment and handle them at a later point, but nobody restricts us to only take the first layer around this box we ignore. We could also ignore more layers, and the question arises, why would I do that? The reason is very simple. The closer the boxes are, for example, if you take the box here, A, and any box outside, and this would be one of the closest boxes, the more elements in the expansion I would need, and therefore one could argue for a larger separation criterion, I could reduce the number of multipole moments. So this is another parameter that technically is has to be chosen in order to compute. What we do with the particles that are nearby inside these gray boxes, we would do a classical direct summation, and if our particle system, like in MD, is homogeneously distributed, the number of particles in the near field, so to say, so everything in the gray thing is near field, would be constant, so there wouldn't be an n squared overhead. But you could already see that if we increase this WS to infinity, everything would be near field. So obviously the optimum is for small WS and not for high WS. So this is parameter number 2, tree depth, separation criterion. And the last parameter is basically the length of the multipole. So how many elements do we use in a multipole expansion? And we decided for a representation with spherical harmonics of our multipole representation, because it's the most compact form you can get. And basically the only thing you need to store for each box, and a box contains particle, and to represent these particles you would need to store is a triangle, like you can see here. And the first element of the triangle down here, where L is 0 and M is 0, this would be the monopole of your box. And the next two elements would be the dipole, and these three elements would be quadrupole, and so on. And we can do that up to, I would say, arbitrary order. It's implemented currently until order 50, so 50. This is quite substantial, and would only be needed if you need the full double precision or something like this. If you're computing with just floats, you need usually less, and it also depends on what you want as a user, as a precision. Each of these elements in the multipole expansion basically is represented by a complex number. And we have matrices or these triangles for each box, once in a form of a multipole moment, and once in a form of a local moment. And again, the size of the triangle is defined by the order P of the multipole expansion. If I want a low precision, I would choose a small number of P, I don't know, 2, 3, 4, 5, something. And if I want a higher precision, I would go up, I don't know, 25 or something like this, depending on how much precision I really need. Okay, so as I said earlier, the unfortunate thing with the Coulomb interaction is that we cannot neglect them. So it's not possible to just take the surroundings of my particle and just have like a cutoff method. And with the classical summation, so this is just a simple formula for the energy, you basically, it's like a switch, right? You either solve it or you don't. So you either get it in the precision the machine has, minus the numerical errors, the summation errors, or you don't. So there's nothing in between. But what you usually like in simulations, you wanted to compute it up to a certain precision. You don't need the full machine precision, so it's more like a dial. Depending on your use case, you want low precision, high precision, but you want something to tune. If you say I only need, I don't know, 3 digits in my forces, right, just give me 3 digits in my forces, but do them as fast as possible. And obviously, if I need more digits, if I need more precision, it will take longer, but then I will get more precision. So basically what I'm saying is, what you actually want, you want to solve it as accurate as necessary, but as fast as possible. And the nice thing is, since we now have introduced these 3 parameters, it's very let's say easy to tune it for each and every application, so you get the precision you want and in the fastest time that's possible. Unfortunately, if you would do it yourself, if you would implement it, as I just said, and then you think about how to tune these parameters, it's more like flying an airplane than than simply setting a set of parameters, because unfortunately all these parameters depend on each other. So if you increase the number of multiples and then you do something with WS, or you change the tree depth, this will affect your precision. So this is really, really hard to do, and the problem is basically much harder than solving the FMM itself. So there's no optimal parameter set known analytically. So you have to either do it by hand, or this is something we did. We provide with the FMM runtime and error bounds that can be set automatically by defining a certain error of the method. If you look at the FMM like in a black box like this, usually you put in some coordinates, so that's your particles, and some charges or masses if you do astrophysics. Then the red thing is the stuff you have to set up: the depth of the tree, length of the multipole, separation criterion. And then you have like two distinct things you do. One is something in the far field where the multiples basically can be used to compute the interaction, and the near field, the ones we just skipped for the close by particles. And the far field then is divided into 4 passes, and the near field is basically depending on 1 pass. And at the end, you will get potentials, forces, and energy. Okay, so how does the algorithm look like? So if we go through, why is it order n? Can we explain that at some point? Okay, let's start with pass 1, because obviously we need to somehow translate these particles into multiples, and this is done in pass 1. And since we touch the particles only once and generate a triangle, which is basically of a p-squared shape, the complexity would be n p-squared. We do that for every particle just on the lowest level. And if you look at the same picture inside the tree, we would work inside here, the lowest level. I just chose a depth of 4, and then we would have multiples for each of the particles residing in the lowest level box. That's all that's has been done for pass 1 yet. Okay, so what's the next step? The next step is also part of pass 1. We now shift these multipole expansions up the tree, and there's like several kinds of operators available. The most precise have a complexity of p to the power 4, and there's a better one, p to the power of 3, a cubed one, which is a bit more involved, and we will talk about this later. But basically, you have to choose which one you choose. And the reason why you would choose one over the other, obviously, if the number of multiples is really high, you would choose the one with the lower complexity in order to be compatible with other methods. If we look at the grand picture, it would look like this. So all the multiples in each box would be shifted up with an operator to its parent box and then added up. So these two things here from the gray box at the lower level and the other sibling would be shifted up to the red box, and they would generate a new omega for this box. So we don't touch particles in these level up the tree. We just touch multiples. And if you define a work of f of 1 at the lowest level, you only, since it's an octree, you gain 1/8, 1/64 of work with each level. So, and if you sum that up, you basically have a constant, and so it still has constant complexity shifting these things up the tree. And you do that for every box, and basically you're done with pass 1. Pass 2 is the meat of the whole algorithm. This is where the interaction really takes place, and what we do is we have a certain interaction set, so a certain set of boxes, so geometrically defined, spatially defined, that can interact. And this is just drawn a subset here. So we have to make sure that the gray box doesn't interact with its nearest neighbors, the whiteout boxes here, but it instead interacts with boxes beyond that minimal distance. And for this, we also have operators in p to the power 4 and p cubed complexity. And since we're now translating multiples into local moment, this operation is usually called M to L, multipole to local. If we look how this looks in a tree, for example, on the lowest level, if we pick this box and we want to generate a mu in here, we would take this box here and these two boxes here. There is a rule to that. I'm not going to explain the rule, but the set of boxes that interact on each level is basically limited. In 3 dimensions, it's 189. As you can see, in 1 dimension, it's always like 3 boxes that interact. All the boxes that are further away are not taken into account. They are done on a higher level, and we basically do that for all the boxes in the tree. So not only on the lowest level, but for all the boxes in the tree. So this would be step 2. So before we had just an omega, now we have a mu, and what the next step entails, since we shifted stuff up the tree, we also shift things down, and for that we have the local-to-local operation, which uses a multipole in a certain box and distributes it to the children one level deeper. Again, operator complexity. You have the choice again, and if you look at the tree and pick a certain mu, you would use the mu that's stored in here, shift it down, and add it to the one that's already in here. So you end up with all the mu's coming from everywhere of the tree inside the lowest level boxes. Okay, pass 4 is the final pass of the far field, where basically the far field forces, potentials, energy are computed. This only happens on the lowest level. This is basically where we go back to the particle view. So now you can see in the complexity the number of particles is already included. And since we take this information from our Taylor moments, which have this triangular shape, the complexity would be n p squared, and we would get the forces with that. I mentioned earlier that we dropped some interactions because nearest neighbor couldn't interact. And also particles inside a box on the lowest level have not been handled yet. And this is where the particle-to-particle interaction takes place. It doesn't depend on n in a sense, because we only have a subset m that should be constant. Interacting, and this works for all the boxes in the for all the particles in the box and for all the surrounding boxes and particles within that set. And yeah, with that we are basically done with the FMM, doing the near field only for the certain subset here. We do it for n particles, but since the neighborhood is has a constant number of particles, it's n times n, and the method ends up to be linear. Of course, you can construct, let's say, particle systems that bring down the FMM, in a sense that if you have very skewed trees, that only one box is occupied on each level, and you have very, very deep trees. But any other method that relies on space division would also get in trouble there. So yeah, I've not seen a case where this is really negatively impacting the method. Okay, a short overview about the method. So what's in the Skafakos library, Francisco also talked about. So basically, with FMM, it's possible to compute forces in linear complexity. We also have like 1, 2, and 3D periodic boundaries. We don't yet support non-cubic lattices. For the moment, everything is cubic, but this is work in progress. Since we had a project with the people from Gromex, they introduced a lambda or protonation state, so lambda dynamics for Gromex, and they have their own version running on a GPU based on the FMM. The good thing about the FMM is that we can provide some runtime optimization and error and drift control, so the user doesn't necessarily have to set the parameter by themselves. You can just say, hey, I want a relative error of, I don't know, 3 digits, 4 digits in the energy, and the method will automatically tune the FMM parameters in a sense that you will get optimal runtime and optimal precision with that. We do have optimized operators for CPU and GPU, but this is also still work in progress. And what is currently going on, we basically, when you download the Skafakos library and you look at the FMM, you will see that there's a Fortran version. And what we did at the moment, or for the last years, and it's still ongoing, we ported the code to C++ 14 in order to be more flexible, and I will go into details why this is necessary. Yeah, and at the bottom you can see the support for point dipoles and non-cubic lattices is also something we're working on. With respect to multiple methods, this shouldn't be too hard because dipoles are already included, but it needs more tests before we ship it to the users. Okay, since the talk was FMM towards Exascale, I wanted to talk to you a little bit about the P3 operators, so you see where the problems arise. And I want to especially talk a little bit about vectorization. We don't go very deep into details, but just that you see that there are some issues that need to be solved when we go to Exascale. And the question mainly arises if you talk about readability and maintainability of the code, right? I mean, for years, if the new platform has come up, one would have just wrote another part of the code and another part of the code, and the code was just blown for each and every architecture. And I think this is not sustainable for the future. So what we basically want is, so to say, one kernel to rule them all. So we want to write one compute kernel in a high-level language, not with any intrinsics or any, I don't know, crazy pragmas or crazy directives that fiddle around with the code. And we want to reuse it for different precisions, float, double, whatever you can think of. But we also want to use it for different SIMD widths. So it could be that you're using, I don't know, AVX512, you want to use it, the same code, or you want to use SSE or anything that might be around the corner. Otherwise, one would have to port the FMM over and over again. And the question is, can we write like a portable abstraction layer? And the non-trivial question that arise at this point are basically, why does the compiler do it, right? I mean, I just give it the code and shouldn't it do it themselves, right? But how does it look on a different platform? That's also something. If it works on Intel, I don't know. Does it work on ARM or does it work on a completely different thing, RISC-V? I don't know. And as I already said, is it possible to introduce a portable abstraction so we can use vectorization on this multitude of machines? And the question, does it introduce overhead? And we will look a little bit into that. All of that is pretty trivial if the compiler sees everything and the data structure looks simple. But what do you have to do if the data structure is not trivial? And this is the example I want to give you. And our not trivial data structure is basically a multipole expansion, right? So if you look at the data, it starts with one complex number down here, two complex number, three complex number. You already see that doing vectorization over these elements either ignores a lot of empty spaces, or I don't know, you have to reorder stuff. And the question is how to do that efficiently. So I mean, a triangle obviously is something that isn't well prepared for vectorization, especially if it's a small triangle. Just imagine you have like p to the order 5, 0, 1, 2, 3, 4, 5, something like this. If you have a triangle that's that small, you already see if you have a vectorization width of 8 or 16, what can you do? This is just not the way to handle it. And unfortunately, it also depends on the pass of the FMM, right? I showed you this picture before with these 5 passes, and the first pass and the last pass and pass 4 are fairly easy to vectorize, and the reason for that is they involve particles, and we have a lot of particles, usually more than we have lanes in the SIMD vector, so therefore it's I say more easier to do, but the problems arise where the FMM really shines in pass 1 to 3, where we deal with these multipoles. The picture I just shown you there, it's really hard to vectorize. And we will take a little look at this so you understand what has to be done and probably what has to be done in other codes for Exascale as well. In order to explain that, I have to tell you that if we use these p-cubed operators that have the best complexity, that's the one we want to use, they share the same code path, and that's really cool. So they all consist of a forward rotation, this is step 1, then of a shift of the rotated input to rotated output, and then a backwards rotation. And if you think of all these things, you have to think of memory layout and temporary. So if you do these operations, you really have to make sure that everything fits in cache and so on, and we will take a look at this. So from the bird's eye view, if you want to do a p cubed operation, and you have box A here and box B here, and this vector is not aligned with the z-axis, which would be this box here, you need to rotate the multipole in order that the shift is along the z-axis, and once this is done, you can shift it with p cubed complexity, and then you have to rotate it back. And all of these things, as I just said, are p cubed complexity. So yeah, it consists of rotate, shift, and rotate back. So what's the problem? The problem arises if you look at the loop structure, and I stripped the slide from everything disturbing. So basically, all you need to know is you have a nested triple loop that uses some rotation operator with 3 indices, some input with 2 indices, and you get an output with 2 indices. Obviously, the input is like a complex of real, and real could be float or double or long double. And this rotation operation works differently on the real and the imaginary part of the input. And if you look at it graphically, because I think that's much easier to look at, this would look like this. So this is our operator. This is our rotation operator. This is this nice pyramid here. This is our input multipole, and this is our rotated multipole with respect to the elements. So if you put 5 by 5 elements in, you will get 5 by 5 out, and you will have a matrix 5 by 5 by 5 that does the rotation. And in order to compute the element here where the mouse pointer is, you would need the element here, and you would use the input element here. And for the next 2 elements, you would use the second plane in this operator. For the next one, the third plane, 3 by 3 elements, 4 by 4 elements, and 5 by 5 elements. So you already see that the complexity within this operation changes dramatically depending on what the indices L, M, and K is. So this is obvious that this is hard to vectorize. So what's the bottleneck? And now it's a bit technical. If this is not 100% clear, it doesn't matter. If you look at the Intel platform and you do fused multiply adds, you have a latency of 5 cycles, and you can issue like 2 of these fused multiply adds per cycles. But you also have a memory bandwidth, so you cannot do this for arbitrary data. You can only do a single floating point operation, so an FMA per 2 memory loads. And the problem with that is our rotation matrix is really large, right? If you look back at this picture, this is like P cubed memory that you use at some point. And if you load it all the time, then obviously you waste cycles. If you look at the single input, so if you look at one of this element here or one of this element here, you cannot reuse parts of this matrix. So each element of this matrix or this pyramid here is used once to compute all of these elements here. So there's no reuse in this matrix. So that's another thing that's really bad. If you want to improve that, you obviously have to reuse the rotation matrix. And for that, you need to rearrange your data structure. So instead of an array of structs, you would go to a struct of array. And then you need to stack them, and you need to reorder them. And ideally, you want to do that on the fly, because I don't want to see that in the code, right? It already looks messy. Just imagine you would have to rewrite the code for each and every SIMD architecture. It could be 8 wide, it could be 16 wide, it could be 32 wide. And if you have to write it for each and every of the SIMD length, this would be just a mess. Okay, so what do I mean by struct of array? Or in this case, a struct of complex. So each of this multiple moments or local moments consists of, each of these boxes here consists of a complex number. So real part, imaginary part, real term, imaginary part. So this is basically a struct of complex. So each blue box is a complex, and we have a struct of complex. And since we have many multiples for each and every box, at the end we end up with an array of struct of complex. So AOSOC basically. And we have many of them, as many as we have boxes. And what we can do now is we can reshuffle them. So graphically, this looks the same. It's just like gluing them together on this face here, but the layout changes. Now in memory, the layout in memory for this thing goes like this. So first element, second, third, fourth, fifth, fourth, and so on. But if we go to this struct of complex of array layout, it would change to basically these elements first, then the next one, then these one. And inside the elements, we also need to shuffle around all the real parts together and all the imaginary parts together, because remember, the operation deals differently on real and imaginary parts. And if I would have real imaginary, this wouldn't be a nice SIMD operation. I would need to shuffle. And so there's good use of doing it like this. So if you do that, you could write a stacked forward rotation operator like this. And if you wonder, like, hey, did you have an error on your slide? This looks exactly as the slide before without the stacking. That's exactly right. Basically, what we did hide everything, all this information in the data type. So I didn't show you what the data type of input looks like. So basically, this is like a complex of stack of real, and you already see that this does get pretty much involved, and we are trying to hide the implementation from the algorithmic structure. So from the viewpoint of the code, the user sees the classical implementation as you would see it in a mathematical paper. But what is behind these data types, that's where basically the vectorization works. And you might ask yourself, why can't the compiler do it themselves? If you go back and you see that you come from a structure where you have real, imaginary, and you have to go to a set of real parts and a set of imaginary parts, you can already see that the compiler is probably not capable of doing that. And yes, he's not. Yes. So how does now a stacked SIMD forward rotation operator look like? So before we dealt just with one triangle and the rotation matrix, and now we're dealing with a stack of triangle. So what would basically happen now, we would use a SIMD operation on, for example, these 4 elements, the real part of these 4 elements, with one part of this pyramid, and we would get out 4 results for this line here. And since they are nicely ordered in memory all together, and we tied them together in a struct, we reuse basically this thing here for 4 interactions or for 4 boxes in a SIMD way. So now we basically got our reuse. And since we didn't define or predefine the size of the stack, which is something we can decide at compile time as a template parameter for the C++, we can define arbitrary length. So even if you would have, which would be weird, but even if you would have a SIMD length of a prime number, this wouldn't be a problem, because then the length of this stack would be just exactly that prime numbers or multiples of that prime number. Okay, so what are the timings? That's probably the most interesting thing. And if we go to a platform that has a large SIMD width, unfortunately, it's not developed anymore. But even on the Xeon server CPUs, you will have AVX512, and this is the base. So what you see in the graph is this is the baseline time for the operations if you do it in a non-stacked way, in a non-SIMD way, and we normalized it to 1. And if we do a SIMD stacking and we do a stack of 16, because that's what AVX512 is capable of, we get an improvement of already 3.16. And we get it rather early. So if we have like 100 of these operations queued together and keep the cache hot, then we will get down to this 3.16. On average. And you probably ask yourself now, well, if you stacked like 16 things together and you only get a factor of 3, where's the rest of the time missing? And if I draw the diagram a little bit different, if I draw it without the reordering cost, because that's something I didn't talk about, if you reorder on the fly, because your data structures look like this, and you have to do it for each and every element, you obviously have costs. If you don't count the costs just to check how good the algorithm works, you will see the factor of 16. So if you do a SIMD stack and then unroll even some more, so basically have like 2 SIMD stacks as a stack size, then you will get your factor of 16. Starting, I don't know, at 120 operations that you can do. But as I said earlier, you have to always keep in mind that if you do that on the fly and you cannot pre-store these things, then you lose again and only end up with an improvement of a factor of 3. So that's why I'm saying this is not done yet, because we need to somehow move this stack further and further from the operation away, so that we don't pay these costs, that the reordering happens less often. But that's also ongoing work. But technically, one sees that it's possible with modern C++. Nice templates and clean code, that the compiler can do it automatically. So we didn't basically provide SIMD intrinsics for that. He did see from the code that he could use it, and if I would show you code, you would see that this would be like optimal code. There's nothing in between that costs that you pay for that you didn't ask for. Yeah, if you want to go on a new platform, you have to obviously check for each and every position. you probably should also check all the parameters you would set at compile time if they really behave like they should. Try with different compilers. We checked usually the candidates like Clang or GCC work really well, but Intel sometimes has hiccups, which is somehow weird because they are the vendor of the hardware, but the compiler is not as capable to generating that good of a code. It's getting better, but you have to make sure that it really works with all the compilers. And of course, these optimal parameters might also depend on the length of P, because you have different cache sizes. So this is something you can play around, and if you have abstracted away, that's an easy job because you don't have to change code. Yeah, and the conclusion for the vectorization part is basically you have one code for scalar and arbitrary stacked vectorized code. That's really good. You can reuse this rotation matrix. There's no way around it, so you have to call it. So the best thing you can have is reuse it as often as possible. And as said earlier, you can use even crazy prime SIMD width if that's possible, if that's needed, because the stacking is defined at compile time. The costs you pay is the reordering of the p squared multipole or local matrix. That's something you have to think about, but yeah, we're trying to move it even out more so that the reorders don't cost that much. Okay, the third topic I want to talk about is the infinite parallelization. Up until now, I was talking about the let's so to say intercore parallelization. So you don't need any parallel things despite a SIMD. So, but if you go on a cluster, you usually also have like fat cores with, I don't know, if you look at AMD, 128 threads or something like this. So this is also something I'm very interested in on what we can do with the algorithm with that. And now the problem basically arises. If you look at the software, or a lot of the software that is around, and this is even true for our software, that's why I'm drawing it like this. It's a little bit of a like a glass or this cup of sprinkles, right? So you have your algorithm, and then you started out adding some MPI here and added some threading there, and then you learned about unrolling or instruction level parallelism, and you did something to some loops to improve that, and then you have some pragmas for vectorization, and now you have also GPUs, and everything is basically cluttered together. And if you go to a new platform, you modify the code over and over again, or you even have a full separate branch, and that's not sustainable. What you technically would like to have is something like this. Each of the layers should be really, really separated. So there should be interfaces, obviously, between these layers, but the vectorization shouldn't mind about tasking, for example, or shouldn't mind about MPI. They should know, in a sense, that if a task is vectorized, well, that should be capable of, but it shouldn't be cluttered together. So, and that's where software engineering basically does come in. So that's also the reason we have quite a few computer scientists in the group that are not real experts on FMM, but are real experts on their domain, computer science and parallelization. And this is where we try to decouple the FMM as possible, as much as possible from the underlying architecture. So what we want is basically an abstraction of all the hardware features that are coming with the parallelization, right? You have vectorization, which is in core. You have threading, which is on the node, and you have MPI, which is between the nodes. And then you also have GPUs. And if you clutter it all together and the new platform comes around next week, then you basically start over again. And that's also the problem if it's like an n times m problem, right? We have all these 4 clusters, and architecturally they are all different, and we want to support like applications from plasma physics, molecular dynamics, and astrophysics. And the only way to reduce all these n times m, let's say, complexity to optimize for each application on every machine, basically introducing an algorithm abstraction layer on top and a parallelization abstraction layer on bottom, which is independent and can also be exchanged, right? If we write something in the parallelization that's obsolete in a year or 2, and we can plug it in from a library that can do it better, even better, right? We are not tied to, we don't want to be tied to something that's not developed anymore or that doesn't perform that good. And that's what we are currently doing. We are trying to dissect each and every part of the algorithm into really, really small pieces that can be tested separately. And we are also trying to dissect the or decouple the parallelization from the actual algorithm. So we don't want to introduce, let's say, machine-specific parallelization things into the code. It should be done in an abstract form, and one abstract form we will talk about in a second. There's also one remark about HPC is not HPC. So if you have a timeline like this, ranging from the nanoseconds up to hours, and you see a CPU cycle is less than a nanosecond, network latency is microseconds. And if you look at some applications and the critical wall time, so for example, one time step in astrophysics, then you see that this one time step usually is because astrophysics probably use large particle ensembles within minutes, and deep learning, if you train a set or something, probably within hours. And if you look at different applications, like not even coming from HPC, but high frequency trading or game development, they're all around a millisecond. And unfortunately, the critical wall time for MD is around a millisecond. And why is that a problem? Since most of the people, or at least the people I was talking to, are not interested in very, very large systems like in astrophysics, we need strong scaling. So weak scaling just by increasing the system size doesn't add up. So if you need strong scaling, you need to get all the performance out of it, because yeah, you just shoot with more hardware on the same side of the problem. So strong scaling is basically a must. And you need performance portability. So if you move from one machine to another, you don't want to reinvent the wheel and restart coding. So that's also something that's important. And the second thing is that's basically, obviously, it's a little bit easier to parallelize something that runs in a critical wall time of a minute down to a second than something that runs already in milliseconds down to even less milliseconds. So this is basically where the real hard part with respect to parallelization comes into play. But to be honest, at some point, all the problems move towards this critical wall time, because there's no end with respect to parallelism on the horizon. So all problems eventually at the end will have to have strong scaling. And if we look at the, to go back to the FMM, at the parallelization potential of the classical algorithm, so the n-squared algorithm, the one basically you can do in school, and you draw it like this, you have the input and the output, and there's lots of independent parallelism, right? So you can compute all the forces independently, just read particle coordinates, compute these square roots and divisions independently, and that's great. The disadvantage is the n-squared complexity, but the good thing is at least it's easy to parallelize. With the FMM, we're exactly on the opposite range of the spectrum. The algorithmic complexity is low. We have all-around complexity. Yeah, that's good. But the parallelization is hard. And the reason it's hard is we have many dependent phases. So the phases you can say here are basically pass 1, 2, 3, 4, 5, and so on. And to make things even harder, the amount of parallelism that can be harvested from is varying between these different parts, right? So even if you would run a problem where you have like all the parallelism available, these parts would be the blocker, because there's only one big chunk here and one big chunk here where you really can parallelize. So that's a problem. And if you look at these coarse-grained, I would call it coarse-grained parallelization approaches, you also have desynchronization points. And that's the usual way people did for a long time, parallelize their code on a node, just slap an OpenMP Pragma parallel 4 or something over that, and then inside the loop, you do your computations, synchronization point, next loop, and so on. But the problem arises once there is a phase where there's, let's say, not even little parallelism, but no parallelism, because that's the limit where you will end. And the question is, can we do better for that? And if you look at the independent parallelism in the FMM, you can do a qualitative chart like this. For the first thing, the P to M, yes, it's high at the beginning, great. M to M, it is high, it starts and then it goes down. M to M is high, and so on. So you see these bottlenecks here. The start of M to L and the start of L to L are the ones where we have low independent parallelism. So we're basically waiting on the root node with respect to our octree. And this is something we need to circumvent. And yeah, the synchronization at some point will get problematic. But if we look at the tree separately and not by passes, if we look at these independent little grains, for example, one shift up the tree, one could argue that all these things could be done independently, and we could do other things from other parsers independently if all the boxes down here or all the boxes on this level have been finished with their task from this certain parse. And that's why we came up with a data flow. So we are basically not looking at the whole loops anymore, but only the fine grains. And if you do that for each and every parse, you see that you can basically generate tasks of a certain size, really fine-grained tasks that you can compute independently. This works for all the parsers of the FMM. If we go up, if we go down, if we go horizontal. And we can basically use a tasking approach to overlap these things. And even going up the tree is not an issue anymore, because on the lowest level, there's technically the most work, and there's always something we can overlap, which wouldn't be possible in a loop-based parallelization like this, because the code wouldn't be at this point. And this is something you can do with a task-based approach. So how does the HPC landscape look today? The good thing is there's a new fancy hardware to play with. There's a lot of stuff around, different vendors, different possibilities. Flops are very cheap, so you don't need to optimize for the last flop. But there's also a large opportunity to mess up, because what works well on A, if you, for example, say Intel, doesn't necessarily run well on B if you look at ARM, or even on AMD EPYC nodes or something like this. So you have to tune for each and every of these machines. And the biggest problem is that the peak performance is limited to only a few algorithms. So if you do everything yourself, you probably will be far off from everything, because the algorithm is just too hard to program or to parallelize. And if you make a plot of maintainability or readability of the code and performance, what you want obviously a high maintainability, and you want high performance. So that's the ideal goal. So how to get there? What's the tool, or what's the language? Is there something like this? And obviously, the best performance you will get if you write everything in assembly, but nobody does it anymore. And if you do that, you're highly dependent on the machine, so you don't want to do that. You obviously wanted to do something in a more abstract way, which would be, in our case, C++. And then the question arises, who does this step? So going from high maintainability but low performance to high performance, is it part of the compiler, or is it part of the programmer? Yeah, and at the end, it's technically both. You have seen that with the example for the vectorization. If you help the compiler understand what you're going to do, you will get a clean code, and you can abstract the layers away so that the end user can see only parts of that. That's relevant. But this is quite some effort, and you have to bend backwards a little bit in order to get there. And to summarize, the challenges that arise are basically threefold. If you look at the hardware side, and we didn't even discuss GPUs and stuff like this, you need flexibility in all the parallelization that today's machine provide. You have CPUs, you have GPUs, you have instruction level parallelism on the CPU, you have vectorization, you have out of order execution. You could optimize for. You have different caches, different even cache levels and sizes. You probably need to be NUMA aware. You have threading and MPI. So this is something that comes from the hardware. But you also need configurability in the middle section, right, for the algorithm. Just think of these P3 and P4 operators. It might be that the P4 operators is better on a GPU than on a CPU. So you would need different implementations and different critical paths you could execute. And this is exactly what we're doing right now, splitting everything up into tiny chunks that have a defined interface, and we can plug and replace, in a sense, depending on the hardware. Because not all algorithms, or not one algorithm, is best on each platform. That's really important to recognize. And on the highest level, there's also some customization going on in the application. For example, if you change the physical model, if you want to support dipoles, or if you want to change the accuracy or change the system size, this is also something you need to handle. And since this is the world we're living in, we decided to really split the hardware part from the software, not the software part, but from the algorithmic part, so we can have an ease of mind and we don't need to rewrite everything if a new architecture comes up. Obviously, if a completely new architecture comes up, we have to adapt our abstractions, but most of the time it's not a qualitative change, it's more quantitative change. So if you support SIMD, then you're already good for something that goes on a CPU, because if you are data parallel and vectorization is nothing else than data parallelism, you already have something that's useful for a GPU, and there's also convergence on that level. So I would say this is a good approach to go toward Exascale. And with that, I'd like to thank you, and I'm open for questions. Thank you very much.
Thank you very much, Ivo, for your presentation, which was really from the algorithm to the implementation, I'd say. Before I see any more question, I have one myself. So is the FMM mature enough to enter in a classical molecular dynamics highly used code? So are we ready to see a new version of an MD code using FMM rather than particle meshable?
Very good question. So I think from 2013 to 2019, we had the GROMEX project you mentioned earlier, and we worked together with the developer Carsten Kutzner and Helmut Gruppmüller from Göttingen. And we basically talked about exactly that. So what is the limiting part of using an FMM in an MD simulation? And what they basically found out is that if you want to do a more challenging physical model like lambda dynamics or protonation states or something like this, then the FMM has advantages that where the, let's say, crossover point with the classical approaches for long-range interactions is better suited. Because you can reuse some of the operators, and that's what they did. So they have their own CUDA version where they implemented parts of the operators, and they run FMM for parts of the simulation. Another aspect where you're probably going to is the stability of the algorithm. So energy drift. This is also something that's something that we need to discuss, and that's also something we are doing in this group. So Holger Daxel is the one that's working on that, and I could give another talk for another 45 minutes that this is really hard to conserve energy with FMMs if you do nothing. But he now designed a scheme that allows us to control the drift, to basically reduce the drift to zero if you want that. So this would be feasible for MD simulation. So yes, I see a future there, but I also have to say that we first of all need to move over to the new C++ version. That's also something that I want to put back into SCAFACOS, so provide SCAFACOS interfaces with the new version, because all the hardware is moving really quick, and it doesn't help if your algorithm runs nicely but doesn't support all the hardware features that today's machines bring. So that's something we have to reevaluate at this point.
And sorry, why, in your opinion, there is this problem of energy drift in the FMM?
It's not only FMM. So I think every multi-level method, you can also look at multigrid, is even worse than FMM. Technically, it's a good question. There is a multiple order at which there is no drift. So it's not that for all precision it drifts.
It's truncation. It's truncation.
Yeah, it's basically the truncation error, but to control that is really hard, and we now have a way of doing that, but obviously that's also not cheap. Yeah, when one has to evaluate further if this is critical or not. Even while talking to the people that do GROMEX, they were really happy with the multiple order around 8, right? Where there's still drift in our simulations. They said, for us, it's fine, no problems. But you're right, one should have a more general approach to control it depending on what the user wants. Yeah.
Okay, thank you. I see a question from Matthias Kirkart.
Yes, thank you. Can you hear me?
Yes.
Yes.
I have a question. I'm sorry, I only joined when you started the second part talking about the rotation-based M2L transition. So you said you reuse the rotation matrix. I mean, it's different for every angle. So how can you reuse it for different translations?
Short and long answer is like there's like two implementations of the rotation. There's a normal rotation, which basically for this 189 interactions would come down, I think, to 25 or 26 rotation matrices. And what you would do is some kind of binning. So you would have like 26 or 25 of these rotation matrices, and then you would bin certain multiples to their certain angle, and then you can reuse them. Or there's also an approach where you have a fast rotation, where you have a flip matrix, where you use a different rotation. Then you would basically have, let's say, only one rotation matrix that you can that you can reuse for all the rotations, but have a bit more work in the non-p cubed operation. Yeah, there's like two implementations, but this is even harder to do efficiently. That's why I'm not talking about this in this talk. Just think of it as having 26 rotation matrices, because there's like 26 angles coming up, and that's fine.
I'm asking because I am actually working on the second approach you were talking about, the one where you use this flipping. And actually, there is an interesting pattern to this, namely that these flip matrices are only 1/4 filled. And
that's true, but you need two of them, unfortunately, because you have two flips. So the complexity is the same as the one I presented. So runtime or flop wise, you will not see a difference if you implement it ideally, because you've probably seen in my chart that the pyramid I've shown you is also a quarter pyramid, and the only difference to the fast rotation one is that every other element would be empty, but you would need two of them.
In any case, if you don't mind, I would like to talk to you after this talk about this, because
sure.
I'm actually working exactly on this thing at the moment. So yeah.
Sounds good.
Thank you.
Thank you.
I would like to remind Matthias and everybody that the presentation of Ivo, as well as the previous one, will be on the YouTube Protein Electrostatic channel. So if you want, you can have a look at it also for completeness. Okay. Any more questions? If not, then I would like to thank, yes, go ahead.
Yeah, maybe I have a last question concerning the scalability. I mean, you mentioned that that's more or less optimized for as much as you can, and the more a method is optimized, the worse is the scalability, maybe, because the time per degree of freedom gets lower, and the communication overhead increases probably. So, what is your experience then actually with scalability in that sense? And the second question in that respect is, would that be then a good example, for example, for modular supercomputing, where you have parts of the algorithm for a very big application running on one part of the machine, and the FMM on a smaller partition of the whole machine?
Okay, yeah. So to answer the second question first, I talked also to the Gromex people, and what they are doing, all the long range stuff is not computed on all the nodes at all the time. So they're already doing this. They're basically running the long range stuff on a subset, on a 6 or 8 of the core. So this has already been done, because the efficiency isn't that high. So I would agree, depending on the scalability we can provide, a smaller set obviously is always better. But the question is, do you have enough other stuff to compute in time that it makes sense, right? I agree that probably classical MD is not the best Exascale example, in a sense, because it's not. we need strong scaling, and a first candidate for Exascale would be something that you just weak scale. You just increase the size, like the latest QCD people, that they just shoot with more input to the machine, and they can easily harvest it. For MD, I would say that's much harder, and one had to tune it in a sense that parts that don't scale should run on a smaller partition. I agree. With respect to the first questions, I don't really see the point with optimization and scalability. Maybe I should explain again that we really try to separate these parts out. So if you optimize something for vectorization, for example, it has nothing to do with respect to tasking or something like this. So you shouldn't see a difference there. The only problem you have is if you already are at a low execution time or at a good execution time because you're using vectorization. Again, it's much harder to utilize everything in the tasking layer, and again, then it's much harder to utilize everything between the nodes. So that's apparent. But other than that, I don't see an issue.
Yeah, I mean, actually, this overhead of communication, yeah, which you see very much earlier than for, let's say, slow algorithm, or not optimized algorithm.
You're really talking about MPI. You're really talking about over the network, yeah.
Scalability to a large number of nodes.
Yeah. I would basically say, and that's what we're working on right now as well, is if you have a tasking approach on the node that basically can execute each and everything that's available right now and backfill if there's a starvation phase, this would also be true for communication over the network, right? So there's no need to stick with the BSP model where you have a communication phase and then a computation phase. This is also something that we need to go away from and basically have communication all the time. And basically allow, once a package is received, once we get a multiple or local moment from a different core, immediately get to work and do something with it. And I would say then scalability can be improved. But up until now, everything was kind in a lockstep, right? You have a computation, communication, computation, communication. This is still true between time steps, I agree, but at least we should do something about it while dealing with a single time step.
Okay, thank you.
Okay, if there are no more questions, then I'd like to thank again Dr. Ivo Kabadshow for the presentation of today, and we will meet next week on Monday, Monday 20th. Thank everybody.
Thank you.